So, what if I told you that the entire future of technology, I'm talking about the device you're watching this on right now, the phone in your pocket, all of it, depended on one single, impossibly complex machine? A machine so extreme that for decades, pretty much everyone thought building it was just impossible. This machine costs a mind-blowing $400 million for one of them. It is, without a doubt, the most complicated commercial product humanity has ever built. So what on earth does it actually do?
Okay, so its job is to perform a task with a level of precision that is almost impossible to wrap your head around. It fires a super high-powered laser to hit a tiny, tiny droplet of molten tin, about the size of a single white blood cell, while it's flying through a perfect vacuum.
And it doesn't just do this once. It does it 50,000 times, every single second. And here's the truly insane part. They don't miss. Not a single shot. This whole process basically creates a tiny artificial sun right inside the machine. It uses mirrors that are so perfectly smooth that if you blew one up to the size of our entire planet, the biggest bump on it would be thinner than a playing card. So you gotta ask the obvious question, right? Why? Why build something this expensive, this complicated, this utterly extreme? Well, the answer has everything to do with a fundamental rule that has powered our digital world for over 50 years. And the fact that, back around 2015, that rule was about to come to a screeching halt. That rule is called Moore's Law. For decades, it was the reliable engine of our modern age. See, making transistors smaller means you can cram more of them onto a computer chip, which makes our devices exponentially faster and more powerful, year after year. It's the reason your smartphone is basically a supercomputer. So chips are made using a process called photolithography, which is kind of like photographic printing, but for circuits. You coat a silicon wafer with a light-sensitive material, you expose it to light through a stencil or a mask, and then you etch that pattern into the silicon. Now, the most critical step, the one that determines how small you can go, is that exposure to light. The core physics problem really comes down to this. Think of light's wavelength like the tip of a pen. You just can't draw a line that's thinner than your pen's tip, right? Well, to print smaller and smaller circuits, engineers needed light with a shorter and shorter wavelength. And by the late 2010s, they were using 193 nanometer light, and they had hit a physical wall. They couldn't go any smaller. Moore's Law was about to die. So to save the entire future of computing, something radical had to happen. The industry had to place a massive bet on an idea that had been floating around for 30 years, an idea that most experts thought was pure science fiction.
Now, this was not some overnight solution. The journey started way back in the 80s, when a scientist named Hiroo Kinoshita was basically dismissed for even proposing it. U.S. labs picked the idea back up in the 90s, calling it Extreme Ultraviolet, or EUV. By 2000, they had a working prototype, but it was just hopelessly slow. One by one, every company gave up on it, until only one Dutch firm, ASML, was left chasing this impossible dream.
So why did everyone abandon it? Well, there were two problems that seemed to completely defy the laws of physics. First, EUV light is so high energy that it gets absorbed by literally everything, even the air. You can't use normal glass lenses, they just soak up the light. The entire machine has to be a perfect vacuum inside. And second, a powerful source for this very specific kind of light, it just didn't naturally exist anywhere on Earth. The pioneers of this tech faced some brutal rejection. Hawryluk, one of the key researchers in the US, remembers being literally laughed off the stage. The world's top experts told him flat out that it was a stupid idea and it would never ever work. The consensus was crystal clear. EUV was a complete dead end. But against all odds, ASML just kept going. They took on these impossible challenges head on. So how in the world did they solve problems that had stumped the rest of the world for decades? First up was that light source problem. Since one didn't exist here on Earth, they had to start by asking a completely absurd question. How do you build an artificial sun and then stick it inside a machine? And the answer they came up with was even more absurd. They figured out a way to create 50,000 tiny supernovas every single second. By blasting those molten tin droplets with an incredibly powerful CO2 laser, they create a plasma that is 40 times hotter than the surface of our actual sun, and that super hot plasma emits the exact EUV light they needed. Okay, problem solved, right? Not so fast. When you create 50,000 tiny explosions every second, you also generate a massive amount of debris. This tin ash from the vaporized droplets was a catastrophic threat to the machine's priceless, perfect mirrors. Yeah, that debris would instantly coat and completely destroy those atomically smooth mirrors. So their solution was just as extreme. They engineered a controlled hurricane of hydrogen gas to constantly blast the surface of the mirrors, keeping them perfectly clean while the machine runs around the clock 24/7. So with these absolutely insane foundational solutions in place, they just needed a few final, really elegant breakthroughs to push this technology from a crazy science experiment into a real manufacturing powerhouse. The first one was a total masterstroke of efficiency. Instead of one giant laser blast, they started using two. A small, low-power pre-pulse laser hits the droplet first, which squashes it into a perfect little pancake shape. Then, the main high-power laser comes in and vaporizes that pancake. The result? Way more usable EUV light with much, much less messy debris. And the very last piece of the puzzle. It's almost funny how simple it was. An engineer noticed that the mirrors always seemed cleaner whenever they opened the machine up for maintenance. The secret ingredient? A little bit of oxygen from the air. They realized that injecting a tiny, precisely controlled amount of oxygen into the system was the perfect final cleaning agent they needed to let the machine run continuously. So after 3 decades, thousands of brilliant engineers, and billions of dollars, the impossible machine was finally real. And its impact is sitting right there in your hand, in your pocket, and on your desk. This machine can align and print the incredibly complex layers of a modern microchip with an accuracy of just 1 nanometer. Now, to put that into perspective, that is the width of about 5 silicon atoms. It is a level of precision that was once just unthinkable, and it's what allows companies to build the chips that power our entire world. And that really brings us back to the beginning, doesn't it? For 30 years, the reasonable thing to do was to say this was impossible, to give up. But as the writer George Bernard Shaw once said, all progress depends on the unreasonable person, the one who persists in trying to make the world bend to their vision, not the other way around. The story of this machine is the ultimate testament to that unreasonable, stubborn persistence. It proved all the skeptics wrong and saved the very law that drives our technological world. And it leaves us with one really inspiring thought. What impossible things will the next generation of unreasonable minds go on to achieve?